So today you guys are starting a new unit and it's on statistics. I think you're actually gonna like this unit. It's more thinking about it than actual calculations. This will be a long lesson for today, but don't mute me and make sure you listen to all of it because there's lots of little side details that will help you in the end. So make sure you're paying attention to all those little details. All right, the first one is sample space. Sample space is just telling you the total possible outcomes that are possible. So your sample space, you can list it out. You can draw a picture. There's like tree diagrams you can do, a table, Venn diagrams. I personally just like tree diagrams. Those are my favorite to do, and we'll talk about those later on. All right, so let's just do the first one. And you already know the answer. It says find the sample space if you flip a coin once. Well, if you have a coin and you flip it, you already know your possible outcomes, right? It could be heads or it could be tails. So we say our sample space is, and it's a set, so we'll use set notation, is heads or tails. That's it. Now, find the sample space if you flipped a coin twice. Well, if you flipped a coin twice, you know that on the first flip, you could get heads or tails. And then if you flip, say you get heads the first time and then you flip it again, well, you could either get heads or tails. But if you had gotten tails the first time and then you flip again, you could have either gotten heads or tails. So now your sample space is, for flipping a coin twice, is and you could list them out this way. I'll go ahead and just list them this way. You could have gotten heads, 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 tails, tails, head, and tails, tails. Now, did you need to make a diagram for that? No, you could have just thought about it. But for me, I like the tree diagram. It just helps me keep it clear in my head. Okay, so find the sample space for rolling a dice. Well, you already know that. What are your possible outcomes for rolling a dice? All right. Yeah. 1, 2, 3, 4, 5, 6. All the possible outcomes. All right. Notation. Probability. Probability is, well, you already know the probability. Probability is like, what's the probability that I would roll a 4? Oh, probability that I would roll a 4 is a 1 out of 6. It is the number of outcomes in the event that you want. So in this case, if I roll a 4, I only have one outcome out of the total number of outcomes. And there's out of 6. So when we're doing this, this is actually theoretical probability. Theoretical probability says, if I were to flip this coin 10 times, how many heads should I get and how many tails should I get? Well, theoretically, I should get 5 heads and 5 tails. If I actually flip this, will I? Well, I don't know. But I can tell you that it doesn't really matter. The more you do, like if you were to do this to 1,000 times, you would get closer to 500 and 500. So theoretical probability is like what it would approximate over many, 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 many times. Okay, and so that's the probability that we're talking about in here. So exactly, if I flip this coin once, those tails, twice, heads, and I can't flip, 3, 4. So I flipped it 4 times. and I got 1 head when I should have gotten 2 and 2. So again, the more I did, I would get half and half. Okay. All right. Find the probability that you have math 5th period. Well, you have how many classes total? 6. And how many options do you have for 5th period? Well, just 1. So the probability that you have math 5th period, 5th period math, is 1/6. Find the probability of rolling an even number on a dice. Oh, side trick. Let me. Quick vocabulary. It is called 1 dice. If you have 2 of them, it is called 2, 3, 4. What's the plural form of dice? So you have 2 die, 3 die, 4 die. Okay, so the plural form is die, and you have 1 dice. All right. Find the probability of rolling an even number. Well, probability of rolling an even on a dice is you have 2, 4, 6. So 3 out of 6 options. So 1/2. This is important. Next one, you have 2 types of events. You have independent and dependent events. Let's see. The probability that one event occurs in no way affects the probability of another event occurring. So independent events is one does not influence the other whatsoever. So if I have a coin and a dice, if I roll a dice and I get a 6, it has no effect on when I flip this coin. Okay, that's an example of independent events. So independent events are when they have no effect on each other. Okay, like flipping a coin and rolling a die. All right, they are not related events. All right, and we'll get to dependent events in a minute, but first we're back to independent events. So draw a sample space for rolling a even number on a dice or rolling a prime number on a dice. As a quick reminder, what is a prime number? All right, so prime numbers, again, is a number greater than 1, only divisible by 1 and itself. So we know our even numbers are 2, 4, 6, and we know our prime number is greater than 1, divisible by 1 and itself. So I'm just going to go ahead and list all these numbers just to make sure that I don't miss any. And in this case, I'm going to go ahead and draw a Venn diagram. So I have even numbers. I have prime numbers. And then you always have your set to make sure it includes something that may not go in there. All right, so let's go with our, should we start in order? Okay. 1, is 1 a prime number or an even number? 1 is not a prime because a prime number has to be greater than 1. 1 is not an even number because it has to be divisible by 2. So 1 is neither even or prime. So it goes here. 2 is even. it's greater than 1 and only divisible by 1 in itself. So 2 is even and it's a prime. So 2 actually goes there. Okay, that was a trick. All right, 3. 3 is only prime. 4. 4 is definitely even and not a prime number, divisible by 2 and 4. 5 is a prime number. And 6 is just an even number. Okay, so that's another way of doing a sample space. Remember that we said, oh, you could do a sample space as a tree diagram, table, and a Venn diagram. So this is an example of a Venn diagram. All right. So what's another example of two events that are independent? We already did, you could flip a coin and roll a dice. What would be another example of an independent event? Let's see. Ideas? So maybe probability that it rains today and the probability that you watched the video on the day it's assigned. This video. All right. Anyways, you get the idea. Things that are completely unrelated. Days. Okay. And I'm sure you have better ideas. Okay. Next one says, given the following spinners, what's the probability that you spin an even number and a vowel? Spinning an even number. So we have our 2, 4, 6, spinning our vowels, A, E, I, O, U. So it's only O. So the probability that you, and this is sometimes how they write it, probability that you get an even and then probability that you get a vowel is equal to the probability of you getting an even number. If they're independent events, you can actually multiply the two. So probability that you get an even number times the probability that you would get a vowel. So with independent events, you can actually always just multiply. Probability that you get an even number is 3 out of 6. And then probability that you get a vowel is 1, 2, 3, 4, 5, 1 out of 5. Let me go charge my battery. All right, now to solve this, you just multiply straight across. Or you can reduce. If I were to do this one, it would be 3 1/2. So that's going to be 1/10. And that is your probability. If you didn't reduce this, again, anything on top reduces with anything on the bottom. You could have multiplied across, but it makes your math harder. 3 times 1, 3. 6 times 5, 30. And then again, reduce that. 3 goes into 3 once. So you still get 1/10. Either way, okay? But the best thing is to just reduce first and multiply. Next one says, using the bag of marbles on the left, what is the probability of pulling out a black marble 2 times in a row? So this is important. This is called with replacement and without replacement. So if you have the bag of marbles, imagine that you, and I don't have marbles. So let's just say I had dice. Okay, what's the probability that I would, pick a big die? Let's just say, okay, I take the die. Now, if I do it again, well, what's the probability that I would get that big die? Well, there isn't anymore. So, but if you put it back with replacement, then that actually changes it. Okay, so that's what this problem is going to be talking about. Okay, so first let's make sure we understand the diagram. It says there's 2 black marbles. Well, I see 1 black marble. Where's the other one? Okay, it's actually this one because they put like a red X to it, but it looks funny. So we have 2 black marbles. Total marbles, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there are 10 marbles in the jar. So we say our sample size is 10. When you first put the marble back in, so that's going to be with replacement. When you keep the first marble, and this is going to be without replacement. All right, so it says, okay, you have this marble on the back. What's the probability? You're going to take two marbles, right? You're going to get a black marble and then a black marble. That's what you want to get. So you're going to take a marble here, and then you're going to put it back in, and then you're going to take another marble. So what's the probability that you would get a black marble and a black marble? Well, the probability that you get a black, because they're independent events, you can say probability of black times the probability of getting a black marble. So probability that you get a black marble, if the bag is full, is going to be 1 out of 10. You put that black marble back again with replacement. Now, what's the probability that you get a black one? Oh, probability that you get a black is, 2. There's 2 choices right there. You put it back in, it's the same bag, so what's the probability that you get it? Also 2 out of 10. Okay, multiply this across or reduce this, so this turns into probability that you get a black and a black is 1 out of 25. Now, without replacement, so you're going to take one marble out, and then you want to get another marble out. Which probability do you think would be higher? That you would get 2 black marbles when you replace it or when you don't replace it? You're more likely to get 2 black marbles. Let's find out. Okay, and I'm sure you're probably correct. So here you're going to do the same thing. You want to get probability of black and a black. Well, probability of black, the first time you have a full bag of marbles. So the probability that you get a black marble is 2 out of 10. Now, you've already gotten 1 marble. So probability that you would get another black marble, let's say you did get the black, is now there's 1 left in there. And how many marbles are now in there? 9. So that's the trick part right there, is that the first time it was 2 out of 10 probability. The second time it was 1 out of 9 that you had. Okay. And then same thing, you're just going to multiply across. So 1 out of 45. So again, you have better chances here with replacement than without replacement. And that makes sense. Okay. I hope you understood that concept, because that's an important one, with replacement and without replacement. All right, the next one says, what's the probability of getting a red jelly bean on first pick and then without replacing it, getting a green jelly bean on the second pick? Okay, so these are kind of hard to see. So let's see what we have. How many jelly beans are there? There are... Okay, so our size is 12. There are 4 reds. Those are those dark ones, hard to see. There are, and we're worried about the red and then the green. And 2 green. And there's other colors there, but not too worried about it. Okay, so here, probability that I would get a red jelly bean. take it, not put it back, and then I'm going to try to go for a green jelly bean. So this is with replacement or without. This is without replacement. So probability that you get a red one, well, that's easy. That's going to be 4 out of 12. Probability that you get a green, now you've already taken one marble out. And then probability that you would get a green, well, you would have 2 choices out of how many marbles? 11 marbles because, or 11 jelly beans because you've already taken one of those out. Okay, then just multiply straight across or reduce. Again, you could reduce 4 and 12 or 2 and 12. Multiply across. Oops. All right, 2 out of 33. And you can leave it as a fraction or plug it in the calculator and write it as a decimal. That's fine. Okay, moving on. All right, so now we're moving on to dependent events. And dependent events is the probability of one event occurring influences the likelihood of the other event. The likelihood of the second event is determined by what happens in the first event. So again, we have independent events and then we have dependent events. So sometimes they're going to ask you questions about card decks. Before we get to the question, just want to make sure that you do understand how a deck of cards works. So you have all the different suits, and they go from letters A through K. So this would be like your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 13 cards for every suit. So that's your clubs, that's your diamonds, that's your or spades, diamonds, clubs, and then you have your hearts. Okay, if you didn't know that, maybe you want to take a minute and write that down. And so there is 13 of each, and there are 4 different suits. So 4 times 13 is 52 cards. Okay, so you have all of these for each one. All right, first question says, explain why drawing 2 aces from a deck of 52 cards is an example of a dependent event. Well, if you have one ace that you draw, and you're trying to get another ace, now you have less available, so that's why it is dependent. What would be the probability of getting an ace on your first draw? Well, how many aces are in a deck? Again, there would be 4 aces in a deck, 1 for every suit that there is. So 4 out of 52, 1 out of 13, and reduce that. And again, this is going to seem easy to you, but later on some of the details. So just make sure you're listening to all of it. Okay, if you don't return this card to the deck, what's the probability of drawing an ace on the second draw? So let's just say you picked a card. You picked a card, it's an ace. Now you're going to go for another card. What's the probability that you're going to get an ace on the second one? Well, there are now 3 left out of 51 cards because you've already taken out one of the cards. And then there you go. This next part can be a little bit confusing, and it's just more vocabulary for just you guys to know this. Okay, so for mutually exclusive events, I'm going to read all of it, and it's going to sound a little bit confusing, but it'll kind of make sense in a minute. It says a mutually exclusive event is when they cannot occur at the same time. If the occurrence of one event excludes the occurrence of the other. For example, if you toss a coin, you can either get heads or tails, but not both. Another word that means mutually exclusive is disjoint. If two events are disjoint, then the probability of them both occurring at the same time is impossible. Okay, it's 0. If I get tails, then I can't be getting, if I get heads, I can't get tails. If I get tails, I didn't get heads. Okay, they cannot occur at the same time. This, of course, means that mutually exclusive events are not independent, and independent events cannot be mutually exclusive. We're going to go through examples to kind of help you think about that a little bit more. Okay, make sense of it. Draw a sample space to show that mutually exclusive events of rolling a 2 and rolling an odd number. So I'm going to go back to my Venn diagram for this one. I'm going to say I can have, if you roll on a dice, 1, 2, 3, 4, 5, 6. I'm going to have my sample space where I can roll a 2 or I can roll an odd number. All right. 1 is an odd number. 2 is obviously a 2. 3 is an odd number. 4 is not an odd number and it's not a 2. So 4 is going to go somewhere outside in your sample space. So this is still part of your sample space. It just doesn't happen to be a 2 or an odd number. 5 is an odd number. And 6 goes there. Okay, so that's what a sample space looks like, where on the other ones, remember that we had an intersection of the two? Let's see. Yeah, so when we did this one, we did have something that did hold something in common. Mutually exclusive is that they do not have anything in common. They won't have that middle intersecting part. All right, so let's think about these. It says, let's imagine we are rolling this die just once. Can you identify the following pairs of events as mutually exclusive or not? So for this first one, rolling a number divisible by 2 or rolling a number divisible by 3. Are they mutually exclusive, meaning they don't have anything in common, or they're not? So these ones, and here are your options, rolling a die. So what is it? These are not mutually exclusive. The reason for that is you could be rolling a 6. If you roll a 6, that number is divisible by 2 and it's also divisible by 3. So these are not mutually exclusive. Next one, rolling a number divisible by 2 or rolling a number that is divisible by 5. So rolling a number divisible by 2 or rolling a number that is a multiple of 5. Yes, these are mutually exclusive, okay? The only number divisible by 5 here is going to be 5, and numbers divisible by 2 are 2, 4, 6. So those don't overlap, or they don't have, they don't fall into both categories. So those are mutually exclusive. Rolling a prime number, again, number greater than 1, divisible by 1 in itself, or rolling an even number. So, and this one was not, because of the 2. 2 is a number that is prime, and it also happens to be even. Okay. All right, last one. Rolling an even number or rolling an odd number. Yes, these are mutually exclusive. Why? Because you can't be even and be an odd number. You're either one or the other. So mutually exclusive means that you can't have both happening at the same time. So for example, if I drive my car today, well, then I can't be driving my truck. If I drive my truck today, then I can't be driving my car. If you flip tails, well, you did not flip heads. Okay. It actually, it's not possible, right? If I picked the red one, well, then I did not pick the gray one. Okay. So it can't happen at the same time. All right. All right, moving on to Venn diagrams. Now, a lot of the rest of your unit is going to have Venn diagrams. So making sure that you know how to read them is very, very, very important. So first thing you want to do is look at it and see what it's about. Below is a sample size for students taking a foreign language. So there's French only, Spanish only, both. They're taking French and Spanish, and then 6 that these could be taking another language or just not taking any language at all. Very important. The first thing you want to do is find your sample size. So your sample size is 9 plus 7 plus 14 plus 6, whatever that is. So then they say, what's the probability of someone taking French? Well, the probability of someone taking French is all of this. And go ahead and do the shading as well. It'll help you for later. So probability of somebody taking French is going to be that 16 out of 36. Go ahead and reduce it. Probability only French, well, that was easy. They already told you. Only French was just this. Probability that they're taking a foreign language. Probability that they're taking a foreign language is going to be all of these, okay? So even if they're taking 2 languages, they're still taking a foreign language. So that's going to be the 9, the 7, the 14, or easier said, there's 6 that don't, you know it's 36, so it's going to be 30 out of 36. And again, always just reduce your fraction. Probability that they're taking Spanish is going to be anything in here. Probability only Spanish. Probability that they're not in Spanish. So probability that they are not in Spanish is definitely the 6. And if they're taking French, they're actually not in Spanish. So the probability that they're not in Spanish is everything but Spanish. Okay, so you knew it was a 6, but it was also the ones who were just taking French. So just be careful when you're doing these. And again, always reduce your fractions up. Okay. All right, so those aren't bad. Okay, they kind of made sense. The ones that you are most likely to miss this unit are these 2 problems, and or. So Spanish and French? Which people are in Spanish and French? Correct. It's the ones that are in both. So and is going to be they actually have a notation for this because I'll do this for a little bit more complicated probabilities. So the notation for and is this symbol here. So you could say probability of Spanish and French. Let me see if it's not like an N. Let me see if I can find it on a calculator or something so you can see. Okay, so I found it. So you guys can see it looks kind of like, it's not an N, but it looks like that. And then they're also going to do like a U. And then we'll talk about what that one looks like. So, and that actually stands for or. All right. So Spanish or French. Which students are in Spanish or they're in French? So you know the ones that are in Spanish. I flip these. Or French. Does that include both of them? Like if you're here, would you be in Spanish or French? Mathematically, the answer is yes. So Spanish or French is all of this. And they use that letter, it's a union. That's like an intersection. This is called a union. So this is going to be and they would say probability of being in Spanish or French. This one I'll have to explain a little bit more if you're getting confused. Let me see. Let me think of a good example. Okay, so here's a random side note. So let's just say I was giving out drinks. Charlie had water. Tatum had water and lemonade. She had a cup of water and she also had some lemonade. And Ben just had lemonade. If I said who had water and lemonade, well, that's easy. It's just Tatum. But if I said who had water or lemonade, well, he had water, he had lemonade, she had water and lemonade. So yeah, they all had water or lemonade. So this would be including all of them. I don't know if that helped or confused you. Okay, we'll see how this goes. All right, moving on. Okay, last problem. Here we go. So for this problem, it says find how many males and females are right and left-handed in this class. Normally I would ask you guys, but I just made up this data. Organize your data in a table first, then use that to draw a sample space and answer the questions below. And then here they give you the information. Again, as a reminder, there's different ways to do sample spaces. You could have done actually a tree diagram, a table, and a Venn diagram. Well, this one actually works well either way. Probably the table is what makes the most sense to us. So you have a class, you have some boys, you have some girls, and they are left-handed and right-handed. So we have left-handed, right-handed, and then you'll have your totals at the end. Left-handed boys, so a class has 11 boys, and 1 is left-handed and 10 are right-handed. 12 girls, 3 are left-handed and 9 are right-handed. So these are your totals. We should do them in a different color. Okay. And of course, you always want to know how many total in the class, 11 and 12. So it's going to be 23. All right, so that was easy. We just took our information there. Now, here's what you're going to have to do is making sure that you know how to transfer this information onto here. So this is right-handed and this is female. This is confusing. All right. So if this is right-handed and this is female, then the easiest number to go in here is right-handed female. Does that make sense? So this is right-handed female. Okay, because this was right-handed people. This is female. So this has to be right-handed female. So right-handed female is going to be 9. Well, if this is female and this is 9, then what goes into here? Does that make sense? Why is that? So all the females we know are 12. So this whole number has to add up to 12. But 9 of them are right-handed, so the rest of them are the 3. Okay, got that. So in essence, if these are right-handed female, then this is left-handed female. All of this is right-handed, but we know that this is right-handed female. So what number would go here? Well, all of the right-handed are going to be 19, but 9 of them are female, so the other ones have to be 10. Well, if this is 10, then this is actually right-handed male. Does that make sense? Okay. And again, this can be tricky. So the last one I've used the 10, the 3, the 9, the 1. Where would the left-handed male go? Yeah. And this was actual data from one of my classes. I think it was a year ago or something, the last data that I had. All right. Okay, so now I have my Venn diagram. I can actually answer these questions from the table, but I'm going to have you guys try to answer it from the Venn diagram just to get some practice on that. So what's the probability of R? So probability that they're right-handed is going to be 10 plus 9. Out of, what was my sample size today? Oops, I forgot to write the sample size. Sample size is 23. Always do that first. Okay. This one, I don't know that I've shown you what that little symbol means. That little apostrophe is not. So probability that they are not right-handed. Probability that they are not right-handed is going to be, you can actually subtract 23 minus 19, or since you have the diagram, you can also just say it is 4 from 23. Okay, probability that they're not right-handed. Next one, probability that they are female and right-handed. So female and right-handed, well, 9 out of 23. This one, probability that they're female or right-handed, female or right-handed is going to be all of this. Remember, female or right-handed is actually going to be female or right-handed. So it's the 10 plus 9 plus 3. Or everyone except the one. Okay, different ways to think about it. Well, probability that they're not right-handed. Oh, wait. This is a probability that they're female and right-handed. Well, if they're female and right-handed, we know it's 9 out of 23. So probability that they're not is going to be 1 minus that. So you can either just think about it in this case because you have the diagram, or, oh, you guys are off on my graph, or subtract it. So for this one, probability that they are female and right-handed is just going to be this 9. So you can add the rest, 10, 3, 1, and then say that that would be 14 out of 23. Or mathematically, it's going to be 100% is the whole. So 1 minus 9 out of 23. And this is the same thing as 23 over 23. Keep going off the graph. Sorry. Okay, so either way. This page right here is really important because it has a lot of that notation and kind of making sense of everything. So take a minute, go back and just cover up your answers here, and then just ask yourself these questions from the diagram and see if they do make sense to you. Okay, do you understand it? All right. Okay, and then that is it for today's lesson. Again, you also have the table. If you have the table, that's probably easier for you to see. But on your exam and on your homework, sometimes we only give you the Venn diagram. Get practice with the Venn diagram, and then the table actually comes a little bit easier for you. Okay, and then homework, you guys can start on that, and that's it.